Start.
Okay. Good morning. Good morning to all. In the last class, this is welcome to TRA Society online classes, and we are discussing in the last class ray optics, and the introduction part of this ray optics we have started. In that introduction, the nature of light we have discussed, and light form of energy, and also how does it travel. Even though there is vacuum, light can travel, we have discussed, and also different types of spherical mirrors, how they are prepared, concave and convex mirrors, and what is concave and what is concave, and also pole, center of curvature, focus point, principal axis, and also while using the derivations, we have to use the sign convention. All distance should be measured from P, and all the distance along incident ray and heights we have to measure above the principal axis is considered a positive, and below the principal axis should be taken negative. And focus, how you can show the focus. And next one, lastly we have discussed about the relation between radius of curvature and focal length. In that we have taken a derivation, and from the final derivation we have taken 2f is equal to r, or focal length is equal to radius of curvature by 2. Now today let us start the class with derivation of mirror equation. This is one of the most important derivations in this chapter. What is mirror equation? Means the relation between three physical quantities, that is focal length and also object distance, and when image is formed, image distance. The relation among all these three, the relation among f, u and v is called mirror equation. So to obtain image of point due to reflection at a spherical mirror, whether it is concave or convex, we have to consider some important rays. What are those rays? Here we have taken 4 types of rays. You can take any 2 types of rays. Generally, first ray we have considered parallel to the principal axis goes through the F, joining from the point parallel to the principal axis. After reflection, what happens? After reflection, the reflected ray has to goes through F point. Whenever a parallel ray is considered, it has to go from F. That is first ray. Sometimes we can take another important ray passing through C. That is through center of curvature. What happens? Again, whenever a ray is passing through center of curvature, it reflects back in the same direction. You cannot see any reflected ray. The same incident ray and reflected ray, both these two coincide. That ray is passing through C. That ray, sometimes it may be helpful to see the image. Otherwise, you can use the third one, the ray passing through F, as this is just vice versa to first one. That is, a ray parallel to principal axis is passes through F. The third one is, if the ray is passing through F, after reflection, it passes parallel to the principal axis. These three are most important rays we have to consider. Sometimes if you want to see the image, in any case, not these two, general incident ray is considered. Then what we have to draw? That fourth one, the incident ray at any angle at the pole, whatever the angle we have considered, then the reflected ray follows law of reflection. What does it mean? For example, here at 30 degrees, incident angle is considered at P. Then again you have to, that is incident angle. So what is the reflected angle? Both reflected angle and incident angle should be equal according to the laws of reflection. Therefore, reflected ray also you have to take 30 degrees. That is a last one. So in general, while drawing a formation of image, we have to take first three rays parallel to principal axis, passing through C, passing to F. You should remember these three. Now let us see ray diagram for image formation. Here you can see this is a concave mirror. P is the pole. It is better to draw this diagram, all of the students, why it is PowerPoint program, I will talk about this. Every time I can't show this diagram. That's why once you draw this diagram, where is P? And here AB is a object. So whenever object is placed before the concave mirror or convex mirror, it should be considered as U. U is the object distance shown here, the bottom you can see. Next, two rays are considered here. We have discussed 4 types of rays. Among those 4, we have taken only 2 to see the image. How the image is formed? See, first one is AM ray, parallel to the principal axis BCP. BCP is the principal axis, where the object is placed AB, parallel to principal axis, AM ray is taken. According to our discussion, whenever it is parallel, it has to passes through F. So M, F, A dash and D, M, F, D is the reflected ray, which is parallel to principal axis. And next ray we have to draw, that is passing through C. Here we have taken 3 rays passing to C. Again we have to taken it incident strike at N, and again the path is N A dash C A. A C A dash N is one ray. N A dash C A is reflected ray again. But here we have taken AP. AP ray is passing through P. Whenever it is passing through P, that is general one, that has to goes with incident angle and reflected angle are equal according to this P A dash. And fourth ray we have taken, one is parallel, one is passing through this P, and another is passing through C. All these 3 rays, blue colored rays, you can see these are reflected at one point A dash. So from that point you have to draw a perpendicular to this principal axis, which gives A dash B dash is the image. Now there are different triangles are formed above and below the principal axis as the base. The principal axis is taken as base, and different types of triangles are formed. And here in the derivation of this mirror equation, we have to use similar triangles property. The property is angle A. A property is taken. 3 angles are equal in 2 triangles. Those 2 triangles are said to be similar. So in this diagram you see A dash, B dash, F. The smaller one, the image A dash, B dash. A dash, B dash is the image, AB is the object. Therefore A dash, B dash, F, very small triangle, and MPF, M and P. Actually MP is not a straight line. We have to approximately we have to take it as MP as a straight line. Or in the previous we have shown P dash, and P dash also coincide with P. Those we have to consider. So MP here in approximation we have to take a straight line. MPF is another triangle, and at P 90 degrees, at B dash it is 90 degrees. So these 2 are similar triangles. The angles are also equal at F both sides, alternate angles. So these are 2 similar triangles. Those comparing B dash, A dash, height A dash, B dash, and height of this triangle and the base PM. Here height is big triangle in MPF, PM. B dash, A dash by PM is equal to B dash F. First we have taken height ratio, and basis ratio we have writing B dash F by FP. But PM, here you see in the triangle PM is equal to AB. Here in the equation in place of PM I am writing AB. B dash A dash by AB is equal to B dash F by FP. B dash F by FP. This is equation 1. And similarly, another triangle with image. First we have taken with image, small triangle and this one, and now with object. Again, ABP, you can consider a big triangle. ABP is also a right angle triangle, and another one is A dash B dash P. As in this above, we have taken A dash B dash F. Here we have taken A dash B dash P. And again, here also comparing B dash A dash by AB. Two triangles are similar, therefore both are these two are of the same base. Therefore, you can take B dash A dash by AB. Heights ratio is equal to B dash P. This is the base. B dash P by BP. Big triangle base is BP. This is second one. While you are comparing first equation and second equation, LHS side are same. Therefore, RHS sides you can equate. Therefore, B dash F by FP is equal to B dash P by BP. Now, here B dash F, how to calculate this distance means this can be B dash P minus FP. You can write B dash P minus FP as the geometry is observed. You can easily tell like that. Similarly, B dash P by BP. Again, B dash P, what is it? Image distance to the pole of the mirror. So always we have to take B P dash or B dash P. Both these two while you are seeing, that is object to image. That image to the pole. Image to the pole or mirror. The distance is V. According to sign convention, P B dash or B dash P, while you are considering, it should be taken as negative. Opposite to B P dash means actually we have to measure B dash P we are writing. That's why it is opposite to the sign convention. According to it, you have opposite to V, incident ray above AM. Therefore, it is minus V. And FP, actually PF you have to measure. As it is FP, this is also FP is minus F we are writing is this. So minus of minus F it becomes plus. Therefore, according to sign convention, B dash P minus FP becomes as minus V plus F. Now, again coming FP. FP means minus F. FP means minus F. PF is F. So, according to vectors you have taken, or this convention also, that is equal to B dash P. B dash P is again minus V by BP. BP means object to pole, that is P. B you have to measure according to sign convention. You are taken here BP, therefore it is minus V, minus U, minus V by minus U. So here what you have to do, two similar triangles are taken with the image and with object. You have to remember how to write the ratios of the heights. Heights first you have to write two similar triangles heights. Next you have to compare bases. We can get one equation. And again, second, with using with object, you are getting two similar equations and we are getting one equation. Minus V plus F by minus F is equal to minus V by U. Okay. Now let us say that you can write V minus F by F is equal to V by U. Minus is taken out, and here the calculation you can write V by F minus F by F, that is equal to 1. V by F minus 1 is equal to V by U, or 1 is equal to, you bring that V by U that side, V by F minus V by U. 1 is equal to, you can take out V common here, 1 by F minus 1 by U, or 1 by V. You bring that V this side, LHS side, 1 by V is equal to 1F minus 1U, or finally 1 by U plus 1 by V, or 1 by V plus 1 by U is equal to 1 by F. This is called mirror equation. You should remember this relation is very important whenever. Okay. Another important thing is here, just this is only calculation. First you have to compare two triangles ratios, similar triangles ratios you have to compare. You can get two equations, and the distances you have to take from the P point, and then you have to use sign convention. That is over. Then you can get V minus F by F is equal to V by U. Now, after simplification, whatever the simplification I have shown here with the red digits, and comparing this, you can get mirror equation 1 by F is equal to 1 by U plus 1 by V. Another important thing is this can be used for whether it is convex or concave. We have derived for concave mirror. You can use for convex also. But while using this equation with the proper use of sign convention, this equation is valid for both of these, and sometimes for real or virtual, whether the image is formed real or virtual. Why you are telling? In case of convex mirror, we can see virtual images. Even though it is virtual image, you can see this same equation. So you can use the same. And now, just while completion of this mirror equation with the help of the same diagram, I have already told you to note down that diagram. Why? Because here we are going to see linear magnification. What is the magnification formula? From the same, it is defined as the ratio of the height of the image to the height of the object. How much this object is magnified, how much it is increased, its size. That is the ratio of these two, image height to object. This is also known as linear magnification. So M is equal to H dash by H. As we have already seen, A dash P and ABP are two triangles. In those two similar triangles, we can compare object and image ratios we have taken. B dash A dash by BA is equal to B dash P by BP. While in the ABP triangle, the sides, and here heights of A dash B dash P triangle. So B dash A is using sign convention minus H dash. The why you are taken minus H dash, that is image height is negative we have taken. Why? Because image is formed below the principal axis. That is also according to sign convention. There are three important things we have taken. Heights of the images or objects, heights are measured above the principal axis, we should consider plus. Below the principal axis, we have to take in minus. Therefore, the image is formed here below the principal axis. A dash B dash is formed below the principal axis. Therefore, minus H dash by H. H is above the principal axis. Therefore, I write positive, which is equal to B dash P. Actually, we have to measure PB dash, that is image distance. This is B dash P, therefore minus V. Similarly, BP is also minus U. So minus minus get cancelled out. So minus H dash by H is equal to V by U, or H dash by H is equal to minus V by U. You have to, very interesting thing is, sometimes M is positive. While you are calculating M magnification, you can get positive value, then it means the image is virtual and erect. You should remember images are two types, virtual image and real image. What are the virtual image? What are the real image? I think all of you know. When the image is formed on a screen, you can see the image on the screen. That is real image. Always real images are inverted. But virtual images means you can see the image, but you cannot cut on the screen. Those are virtual images. All the virtual images are erect. For example, you can see your face in your plane mirror. While you can see your face, that is virtual image. That is erect one. That image is erect, not inverted. Okay, so M is negative means what? You have to write your comment. It is a real image and also inverted. You should write that also. According to that, you have to remember this is linear magnification. So now we are going to go another property of light, that is refraction. That is important property of this light. You know what is refraction? When a light when a beam of light enters from one medium to another transparent medium, that is important. Not all mediums can take refraction. Some objects, some medium cannot refract, only reflection takes place. But here, if it is only transparent like water, oil, glass, that type of medium, only it takes. Refraction takes place in air. Air also one of the media you can consider. Okay. So when the light enters from one medium to another medium means one medium to another transparent medium, then it bends at the surface at which these two media are separated. That is called reflected surface. Reflected surface means the surface at which the incident ray strikes. So here in this diagram you can see there are two. One is light blue colored, that is it may be water or glass or whatever it may be, you can take, that is one medium, and above incident ray is coming and strike at a point and it bends. Actually the refracted ray is blue colored. Okay, how much angle of deviation, that also you can see. If there is no medium, the ray may go in the straight line, but it bends certain angle. How much it bends from the actual path, that is called angle of deviation. Now normal we have to draw at the point of incident. With this normal, the incident ray makes angle of incident. The angle subtended by incident ray with the normal at point of incident is called angle of incident. Similarly, what is a refracted angle? The angle at which refracted ray makes with the normal at point of incident is called refracted ray. Whenever refraction takes place, as in case of reflection, angle I is equal to angle R. As in case of reflection, we know angle I is equal to angle R. Incident and reflected angles are equal. And second law of reflection is incident ray, normal and refracted ray, all these three in the same plane. These are two laws of reflection. In the same manner, whenever refraction takes place, you can take two laws. One is same as in reflection. First one is the incident ray, the refracted ray, and the normal to the interface at the point of incidence. Three rays I am talking, three lines. The incident ray, refracted ray, and normal at the point of incidence. All should be lie in the same plane as in reflection. There is no change. Second law, second point. This is also known as Snell's law. This was observed by scientist. The name of the scientist is Snell. According to his observation, he gave this law. What is the relation in reflection? Angle I is equal to angle R. But in case of refraction, the ratio of sine angle of I means sine angle of incidence to the sine angle of refraction should be a constant whenever the transparent medium is a fixed one. We are not changing that one. That is called the ratio of sine I and sine R is called refractive index of second medium with respect to one. Here, the most important thing is both these two we have to consider. Understand? From where to where is the incident ray, where is the refracted ray? Both these two media are very, very important. You should remember whenever refraction takes place. Generally, we will take first medium is air. We will send light rays from air. And second medium, glass, oil, or water, or some other medium we place. So, what is the refractive index for which medium? Means second medium, sin I by sin R. That's why we have to write it is represented by small n, 2, 1. 2, 1 means, n means refractive index of second medium, 2, 1. 1 means with respect to first medium. You have to understand. Sometimes you can write n12. n12 means refractive index of first medium with respect to 2. n32, what does it mean? n32 means refractive index of third medium with respect to second one, whatever it may be it is. And sometimes We have to remember some important points here. Here, n21 is greater than 1. For example, you are getting sin I by sin R calculation, that is 1.56. It means greater than 1. Then what does it mean? If it is greater than 1, R is less than I. It means the incident angle is always greater than the refracted angle. So R is refracted angle is less than incident angle. Both are same. R is less than I. It means according to the ray diagram, the refracted ray bends towards the normal. When it is nearer to normal, that value normal to refracted ray decreases. So R is less, I is more. So then where the R is less, in the second medium R is less. Therefore, this second medium is called optically denser. Actually, the refractive index is taken as ratio of velocity of sound in that medium, velocity of light in that medium to the velocity of light in the particular air or vacuum. Understand? So, optically denser means its velocity is reduced. Whenever velocity is reducing, it bends towards the normal. So, easily you can understand whenever the angle is less, whether it is incident angle or refracted angle, in that particular medium, velocity of light is also less. So, optically denser, the velocity of light is less. Okay. Now, if it is vice versa, opposite, n21 is less than 1, what happens? R is greater than I. Means the refracted angle bends away from the normal. R should be greater. Greater means it has to move away from the normal. While it is nearer to normal, angle is less. Optically denser condition we can see. If it is away from the normal, the medium is said to be optically rarer medium. Denser medium or rarer medium. Here we are using the word optically. Why we are using this word? There is a optically, generally we are using denser medium, rarer medium. What does it mean? What is the density? From the density you can use these words. In general, density is different for optically denser. You should remember, don't confuse those optically denser and physically general density of the medium. What is density? Density means mass per volume. Okay, before going to that, we can see that. Just we can see some optically denser and optically rarer words. Density means mass density is mass per unit volume. That we call it as mass density. And here, optical density. Mass density means mass per unit volume. Mass by volume is called density, you know it. And here, optically denser means according to velocity of light, it is denser. Understand? So here, the mass density is different from optically denser object. For example, to understand this, I will tell one thing. Turpentine and water, you are consider these two. The mass density of turpentine is less than that of water. In nature, turpentine density is less compared to that of water. But whenever you consider light velocity in turpentine is more than light velocity in water. So turpentine optical density is more than optical density of water. So general, what we are using mass density, general density, or we call it as mass density is different for optically denser. Some short questions you may ask. What is the difference between mass density and optically denser? Give example or explain. This type of questions you may ask. So you tell these two are not equal. Mass density means general mass per unit volume, but optically denser means it depends upon velocity of light. Velocity of light is less or more. According to that, we will tell optical density. So, for example, turpentine density is less when compared to that of water, but optical denser we are discussing, turpentine optically denser than water. This explanation also you have to remember in this case, and also you should remember the value of refractive index. If it is getting more than 1, it means optically denser. If it is less than 1, the medium 2 is optically rarer. It's just 2 points you remember while doing any short answer questions and we come across any type of question. Now, general examples and some applications of this refraction. You take general first, second diagram, you see a pencil is placed in a beaker of water. How does it bend at the surface of reflection, water surface area? It seems to be bent. Why? Because the light rays has come out from that region, from water to air. So water to denser to rarer. While it coming like this, speed of light is slower, optically denser one compared to that of air. So it seems to be bending. And in this first diagram, you can see in nature, the position of the sun, and while you are standing on the earth, we are observing the sunset and sunrise. Actual sunrise and sunset, actual sunrise time and sunset time are slightly different. Not actual sunrise we are observing. The middle line is horizon. Horizon means straight line, horizontally to the earth surface. Above and below, you are taking two true position and virtual position. The above one is virtual. Below one is true position of sun, that is sun. Here, why we are seeing this sun before the true position? The refractive index of air with respect to vacuum, while you are calculating refractive index, we have to take two things. Light has to come from sun, atmosphere to vacuum to atmosphere or air. So both these two densities are not equal. This air is optically denser than vacuum. So refractive index of air with respect to vacuum, it is 1.00022. So there is a apparent shift in the direction of sun, approximately a change of half degree. As the pencil here shifting its length, it seems to be bending. So how many degrees it is bending? According to the refractive index of that water, we can tell. Similarly here, vacuum and air refractive index is with respect to vacuum 1.00022. So due to this slight difference, half degree approximately, this bending angle, the shifting angle is half degree. So corresponding time with respect to this half degree is about 2 minutes. So we can actual sunset and apparent sunset, both these two takes place at 2 minutes different. We can see actual sunset before 2 minutes. Similarly, the sun shape in the diagram, you can see a oval shape, not circular one. The oval shape of sun is also due to refraction of sun. Okay, the sun is visible a little before the actual sunrise. How much it is sunrise before, you can see 2 minutes. Similarly, we can see a little after sunset. Actual sunset is over, but after 2 minutes we can see sunset. We are seeing early sunrise and after very late sunset. You have to remember, this is due to refraction of light. Can you understand, students? Due to the main reason here, refraction. The refraction of air is, refractive index of air is more than vacuum. First we have to tell that one. So light comes from vacuum to air. While coming to this, due to the change in refractive index of the two media, what happens? There is a shift in sun. How much it is? Half degree shift is observed. Say, due to this reason, the sun is visible a little before the actual sunrise 2 minutes, and similarly in the opposite a little 2 minutes after the actual sunset. Okay, this is about examples, some more examples we can give. This is about refraction. Okay, now next topic in this is total internal reflection. This is a very interesting nature of this light rays. Total internal reflection. Before discussing total internal reflection, we are going to see first what is critical angle. What is critical angle? Let us see here. When a light ray is passing from denser to rarer, you should remember here, underline this sentence. Denser to rarer. Whenever light has to travel from denser to rarer, the angle of incidence in denser. In from where to where it starts? Denser to rarer. Where is I? I is in denser medium. So the incident angle in denser medium, from which the angle of refraction becomes 90 degrees. In rarer medium, refracted angle should be taken in rarer medium, incident angle should be taken in denser medium, while light is traveling from denser to rarer. But this refracted angle should be exactly 90 degrees. What does it mean? It exactly coincides, it touches, grazes the surface of two media, either air and glass. They are shown here. Air to glass, the light is traveling, then glass is denser media and air is lesser dense, when optically less dense than this glass. So light is traveling from denser to rarer. Then we can see the red light, which is called refracted ray, taken reflection parallel to the surface where these two media are separated. Okay, in this case, refractive index of denser media. Here, what is critical angle? First, we have to discuss the incident angle in the denser media. That I is called critical angle, which is represented by C. Understand? The critical angle in denser media at which the refracted angle in rarer media is 90 degrees, then it is called critical angle. The incident angle in denser media is called critical angle. In this case, when it is grazes, while the ray is touching the surfaces, separated out these two media, then the refractive index of second one means this denser one, N21 is 1 by sin C. In this case, we have to calculate just 1 by sin C. Okay, this is critical angle. Now, let us see what is total internal reflection. Actually, we are going to see total internal reflection. So, here, okay, after definition, I will start. This, say, when a light ray is passing from denser to rarer, as in the cases, if angle of incidence is greater than critical angle, what is happening here in this diagram shows the blue line, blue line, which glass to air, we have taken different rays, blue, green, and red. 3 rays. Red light is critical angle, that is theta C. It is represented. One is going into the rarer media, and blue line you can see while it is started from denser media and again coming to denser media. So this is total internal reflection. What is the phenomena while the ray coming into the same denser media? What is the result? Can you use this phenomena in any instruments? What is the general observations in daily life? We can see in the next class. Today we will stop the lesson up to this critical angle of total internal reflection. Thank you for all. Okay, let us finish